In previous videos, we've seen list decoding and local decoding. It turns out that we can combine these two notions and consider local list decoding. In this video, we'll motivate the problem with an application from learning Boolean functions. So here's our motivating problem for this video. Suppose that there is some function g that takes a length m vector over f2 and spits out either +1 or -1. You are allowed to query g for any x you like, but you don't know g to begin with. And your goal is to learn g, or at least learn some approximation g twiddle of it, as quickly as possible. Ideally, you'd like to do this in time polynomial in m. In particular, you shouldn't just query g on every single x, because that would take time 2 to the m, which is not polynomial in m. Okay, as stated, this goal is clearly impossible. If g can be anything, then querying it on some x doesn't tell me anything about what it could be on another x, so we really do have to ask for g on all of the x's. So therefore we need to impose some structure on g to make this possible. One useful way to impose structure is to assume that g is sparse in the Fourier domain. To define that more clearly, we need a few more definitions. So here's a definition of the Fourier transform over f2. For some function, capital G, like the one we had on the previous slide, the Fourier transform of g over f2, denoted by g hat, is another function from f2 to the m, but now it spits out a real number, and it's defined like this. So g hat of omega is equal to 1 divided by 2 to the m of the sum over all x in f2 to the m of g of x times -1 raised to the inner product between x and omega. Just a note here, on this slide, I guess I've decided that this is an omega. I'm probably going to start calling it w at some point. I'm sorry. I'll try to be consistent. Anyway, if you've seen the Fourier transform over the complex numbers, this might look somewhat familiar. In particular, this looks a little bit like the discrete Fourier transform over the complex numbers if you're used to that, except instead of e to the negative I pi whatever, we have this other thing, -1 to the inner product between x and omega. And if you've seen the Fourier transform over the complex numbers, it turns out that similar things hold for this definition as hold for that definition. In particular, we have an inverse transform, so we can write g of x as the sum over omega in f2 to the m of g hat of omega times -1 to the inner product of x and omega. These g hat of omegas are called the Fourier coefficients. And we also have Parseval's theorem, which says that taking Fourier transforms doesn't affect the L2 norm. More precisely, we have that this thing, 1 over 2 to the m times the sum over all x in f2 to the m of g of x squared, which incidentally just happens to be equal to 1 because g of x is plus or minus 1 in this setup, is equal to the sum over all omega in f2 to the m of the square of the Fourier coefficient g hat of omega. Okay, so that's the Fourier transform. If you haven't seen this definition, or one like it before, the important thing for this video is this equation. That is, we can write g of x as a linear combination of these functions, -1 to the inner product of x and omega for different omegas, and the coefficients that we use are the Fourier coefficients g hat of omega. This is nice because these functions are very simple and easy to understand, and this allows us to write any function as a linear combination of easy-to-understand functions. Okay, so let's go back to this slide. We want to learn some Boolean function g from queries, and as we said before, we need to impose some structure on g in order to do that. So here's the structure we're going to impose. As on the previous slide, we can expand g of x as a linear combination of those nice simple functions. And what we're going to assume is that only a few of these coefficients are big and most of them are small. That is, we're going to assume that g is a simple function in the sense that it's a linear combination of essentially not too many of these simple functions. In that case, we can write g as approximately equal to the linear combination of just those functions. That is, we drop all of the terms here, where g hat of omega is small, let's say smaller than some constant tau greater than 0. And we'll write this thing as approximately equal to the sum over all omega, so that the Fourier coefficient g hat of omega is larger than tau in magnitude. In this case, our goal is going to be to estimate the large g hat of omegas as quickly as possible. Again, we'd like to do this in time polynomial in M. In a bit more detail, here's our goal for this particular problem. Suppose that tau is some constant greater than 0. Then our goal is, given query access to g of x, which has this Fourier expansion, so that most of the Fourier coefficients g hat of omega are small. I'm not going to be too precise about exactly what this means because it's not going to be particularly relevant for our coding theory application. We want to return some list, curly L, of pairs omega and y sub omega, so that if the Fourier coefficient g hat of omega is larger than tau, this constant, then omega appears in our list. And moreover, for all omega that appear in the list, our estimate y sub omega is approximately equal to the Fourier coefficient g hat of omega. Moreover, we want to find our list in time polynomial in M. Notice that this implies that the list itself cannot have size larger than polynomial in M, or we'd take longer than that to just return it. Okay, so this is our goal. If we can do that, and if some assumption like this is satisfied, then we'll be able to estimate this expansion, and in particular, this function. So why are we talking about this problem? It turns out that it is related to a problem in coding theory, not surprisingly. So in order to transform it into something that you might recognize as a coding theory problem, let's start massaging this goal. The first thing we're going to do is a simplification that stems from the following observation. The observation is that given a fixed omega in f2 to the m, we can actually estimate g hat of omega fairly quickly from not too many samples. The reason is that the definition of g hat of omega is as an average of a bunch of terms that look like this, each of which are plus or minus 1. We can figure out any one of these terms by sampling g of x, and so we can estimate the average by just taking a random subset of these and sampling them and taking the average of that. It turns out that if you take not too many samples, then with high probability, that's going to be a pretty good estimate for this average. Again, I'm not going to go into too much detail because our meta goal here is to get to the coding theoretic application fairly quickly, but let's just assume that we can do this. So this means that our goal can be to just find the set of omegas so that g hat of omega is large, because once we find that set, we can estimate each one of them fairly quickly. More precisely, we can modify our goal up here in the following way. First, I no longer need to return pairs omega and y omega, I can just return omega. And I don't need to estimate g hat of omega down here. I'm going to additionally give myself a little bit more slack by allowing this query access to g of x to be randomized and asking that this requirement hold with only high probability. Let's say for each omega whose Fourier coefficient is large, we'd like omega to appear in this list with probability at least 2/3 or something like that. And as usual, the 2/3 here is arbitrary. If we could do it with probability 2/3, we can do it with probability 0.99999 by just repeating a few times. Okay, so this is our new goal. Let's clean it up a little bit. All right, here's the clean version of the goal. Given query access to our function g from f2 to the m to plus minus 1, find a list curly L, subset of f2 to the m, so that for all omega such that g hat of omega is larger than tau in absolute value, omega ends up in the list with probability at least 2/3, and moreover we want to find this list in time polynomial in M. In particular, the size of the list cannot be any more than polynomial in M. Okay, we still don't quite know what this has to do with coding theory, although maybe it's getting a little bit closer. We're looking for a list of things that maybe agree a lot with certain functions. But in order to make that precise, let's massage this requirement a little bit more. For simplicity, I'm going to drop the absolute values Basically, you can just do exactly the same thing that I'm about to do now, except with a minus sign in front, and then both of them together, that'll give you the absolute values. But I'm just going to ignore them for now. Okay, so let's consider this condition, that g hat of omega is at least tau. We can write out the definition of g hat of omega, and see that this is equivalent to this big sum being greater than or equal to tau. And now let's recall that g of x here is plus or minus 1. So that means that each term in this sum is also plus or minus 1, depending on whether g of x is equal to this sign flip, minus 1 to the inner product of x and omega. That means that we can write this condition like this. That is, we can replace this sum with the number of x's so that g of x is equal to minus 1 to the inner product of x and omega. In that case, this sum and is equal to 1, minus the number of x's so that g of x is not equal to minus 1 to the inner product of x and omega. In that case, this sum and is equal to minus 1. Notice that this is just equal to 2 to the m minus that, because either this thing is equal or it's not. So we can rewrite this condition as follows. That is, I've just replaced this with 2 to the m minus that. And now we can push some symbols around and get the following condition. That is, the fraction of x for which g of x is equal to minus 1 to the inner product of x and omega is a little bit greater than a half. Greater than or equal to a half plus tau over 2. Now I'm going to define a new function, little g of x, which is just the 0, 1 version of big G of x. That is, little g of x is equal to 0 if big G of x is equal to plus 1, and 1 if big G of x is equal to minus 1. With this notation, this condition is equivalent to the following. That is, it's equivalent to the fraction of x's so that little g of x is equal to the inner product of x and omega is greater than a half, in particular greater than or equal to a half plus tau over 2. Okay, so what does this have to do with coding theory? Basically, this is saying that our goal is to find all of the omegas so that the agreement between the vector of evaluation's inner product of x and omega and some function g, let's call it a received word g, is large, a little bit bigger than a half. AKA, we want to find all of the omegas so that if I were to think of the vector of all of those inner products, its distance from g is not too big. That sounds a little bit like list decoding, and if you remember from the previous video, it sounds a little bit like list decoding the Hadamard code. In more detail, let's recall the definition of the Hadamard code from a previous video. H of m is equal to the set of vectors omega inner product x1, omega inner product x2, ... omega inner product x2 to the m for all omega in f2 to the m, where x1, x2, ... up to x2 to the m is just an enumeration of all of the points in f2 to the m in some order, doesn't matter what. That is, the Hadamard code is the set of all vectors that arise as all of the evaluations of some linear function over f2 to the m. Now we can recast this goal from the previous slide in terms of a coding theoretic goal about the Hadamard code. We saw on the previous slide that this condition is equivalent to this condition, that is the fraction of x's so that g of x is equal to the inner product of x omega is a bit larger than a half, larger than or equal to 1/2 plus tau over 2. And another way of saying that in the language of the Hadamard code is that the relative distance between g, where here by g I mean the vector that you get when you evaluate g at all of the points, and the encoding of w under the Hadamard code, that is this vector here, is a bit smaller than a half, less than or equal to a half minus tau over 2, for some tau greater than 0. That is, we're given access to a received word g, and we want to find all of the code words of the form encoding of omega, so that the distance between g and the encoding of omega is at most 1/2 minus tau over 2. And we want to do this in time polynomial in M. So our goal is to list decode the Hadamard code. We want to find all the code words that live within some ball of the received word. And the key is that we want to do it locally, from just a few queries. In particular, our time budget here is polynomial in M, which is sublinear in the block length of the code. Remember, the block length of the code is 2 to the M. So we don't even have time to look at the entire code word. That's why we're going to have to do it locally. In the next video, we'll see how to achieve this goal.